There are many uses of differential equations in real-life applications: population growth, radioactive decay, spread of disease, looking at rates of cooling and heating, and applications in pharmacology and physics, just to name a few. In this video, we're going to look specifically at one model of population growth called exponential growth. And I know you've had some experience in the past with that idea, but I want to look at that this time in terms of a differential calculus point of view. So exponential growth, remember, is like geometric growth in that as time goes on, the change in the quantity increases. Graphically, that looks something like this. The more we have, the faster it grows. Now, when we develop what we call a mathematical model, what we're trying to do is to come up with an equation that reflects the real-life reality related to that item. So when I say that I want to express our idea that the rate of growth is increasing as the population increases, we can say that mathematically as follows. The rate at which a quantity Q is changing, that's a derivative, dq dt, is directly proportional to, that's a constant times, our quantity Q. We've taken our real-life reality of how some things change and we've turned it into a differential equation which we can now solve. Now, just before we do that, notice that given that in this situation Q being a quantity is positive, if K is positive, then positive times positive would make dq dt positive. And if our derivative is positive, we know that that means that Q is increasing. And we're dealing with the population going up, we're dealing with growth. Alright, so that's consistent with the idea we just expressed. But notice that our model also accounts for when a quantity declines. If our Q is positive, like we say, but K is negative, a negative times a positive will make dq dt, our derivative, negative. And if our derivative is negative, it means that the quantity is decreasing. And so this is called a decay situation. And if we just look at this a little bit more closely, if we think of our K being constant and our Q decreasing, K is negative and Q is decreasing, that's going to cause dq dt to become closer and closer to zero from the negative direction. In other words, we're saying that the quantity is decreasing at a lesser and lesser rate. And there are lots of applications, particularly with radioactive decay, where that is true. And we'll look at an example of that. Now let's solve this differential equation to come up with its solution. So we can do that, remember, by separation of variables. And so I can break that down into like so. And I can integrate both sides. And this is ln absolute Q. I can leave the absolute value off since we are talking about Q being positive. And this is KT plus a constant of integration. Alright, I can isolate Q by raising both sides to the e to a base of e. So this becomes Q, and on the right side I'm going to break that up as follows. If I add the exponents, I'm back to what I had before. And I'm doing that because E, which is a constant, to C, which is a constant, I'm just going to replace this with a new constant called C naught. And what I have here now is my general solution to my differential equation. Let's define the amount at time 0 to be Q naught, and find from that our particular solution. So this is our T, remember, Q of T. If Q is Q naught when time is 0, that makes my exponent 0. That means my arbitrary constant C naught is specifically Q naught. And I can substitute this back into my equation, And so my particular solution is that the quantity after time t is q naught e to the kt. And you'll notice that from our model, from our differential equation, based on our model of growth, that we have established an exponential function. So what we're saying by this result is that if we start with this differential equation, which is based on a major premise of how populations might grow, the rate being directly proportional to the amount there is, we will get this solution. So if you see this differential equation, you know that the solution is this equation. You can directly go from here to here because we've shown this to be true. Here's an example to make that a little clearer. We have a population of a city growing at a rate proportional to the size of the population. Alright, so that first line, that's our model of exponential growth. The rate is directly proportional to the amount of population. And a differential equation of that form, we have just shown, solves into this exponential equation. Alright, so now we have the specific situation we want to make this specific to, so we're going to need to find our constants k and p naught. Well, p naught is our starting population. And if I read through the question here, it says the present population is 500,000. So I can pop that into position right away. Now I need to come up with k, but I need to have another piece of information to do that. So let's calculate the population after 1 year. It says there's a 5% growth rate. If I take 5% of 500,000 and add on the original amount, I can do that quickly by taking 500,000, multiplying by 105%. That's giving me 525,000. I can then take this side condition, plug it in, and solve for k. Time is 1, so 1 times k makes my exponent k. Divide both sides by 500,000. That's 1.05 equals e to the k. Solve for k by lawning both sides. That's going to mean that k is exactly ln of 1.05, which it might be interesting just to see what decimal value that is. .0488. Which you might notice is very close to 0.05, which was the annual growth rate. Now remember that k is what we call the relative growth rate, which means it's the rate of growth on our interval. Now our interval is an infinite one because we're doing continuous growth. You can kind of think of this as being like compounding interest when you compound annually, semi-annually, or monthly. All right, this is the annual growth rate. This is the continuous growth rate. And so k isn't exactly 0.05, but it's close. A little bit more on that later, but let's take our k value and finish this off. Plug it back into here. So the population after time t is 500,000 e to the, I'm going to put the t times k, I'll put that in this order. I'm going to do that because you'll notice that if I have t times ln, I could bring the t up as an exponent on the 1.05, and e to the ln would make my equation 500,000 times 1.05 to the t. And that probably, you will recognize this as the type of equation that you achieve when you work in Pre-Calculus 12 on exponential growth and decay. If you then wanted to make predictions about the future or investigate what's going to happen later, You could plug in, for example, if we wanted to know the population after 10 years. Okay, we're going to round this off because it's going to be some decimal. We have 500,000 times 1.05 to the exponent 10. We get about 814,447 people. Let me just come back to this issue about the value of K in a growth situation being close to the annual percentage of growth. Because of that, what some people do when they're estimating populations, and they're starting off with their formula, P naught, 500,000 times e to the kt, instead of going through all of the work of calculating K the way we did above, what they do is, since the annual rate is close to the actual value of K, what they sometimes do is just plug in 0.05 right there. And now if we wanted to do the same question above, just to compare how the answers are, if T is 10, let's just see how our answer compares. 500,000. Now we're obviously not going to get the same answer because we have a different value of K being used, but it's a value that's close to the true value of K. You'll notice that we get a population that is somewhat close to our original answer, 824,360. And you might say, well, these two are quite far off. Well, it depends on how you look at it. In terms of a percentage of how large this number is, these two numbers are only about a little bit more than 1% apart in error. And if you're estimating populations in which growth rates are changing anyway, they're certainly not 5% annually, constantly, an error of 1% isn't that significant in the big scheme of things. Which is why K equaling 0.5, the annual growth rate, is often used for the relative growth rate to speed up the calculation and get an idea of what the population is. For our purposes, I'd like you to work with the actual value of K to calculate that the way we did above.